Lesson 5 of Chapter 1 is on parent functions and transformations. We're going to talk about 8 different parent functions, and we call them parent functions because they're the simplest form of a function, and we'll talk about 8 different types. So here are the 8 different types. We have a constant function, which, as you can see graphically, is just a horizontal line. The equation is just f of x equals some number, whatever the height of that constant function is. The next one is an identity function, and the identity function is just f of x equals x, and it produces a diagonal line. It produces coordinate points such as 2, 2, and 3, 3, and 4, 4. The next is a quadratic function. This produces U-shaped parabola curves, as you can see, and the equation is just f of x equals x to the second. The next is a cubic function, and a cubic function has to have an x to the third in the equation, and the graph looks something like this. It's half of a parabola going up and half of a parabola going down. We also have a square root function. The square root function obviously needs to have a square root in the equation, and it looks like half of a sideways parabola, as you can see on that particular graph. We also have a reciprocal function. A reciprocal function takes on the form of f of x equals 1 over x, and these graphs have vertical asymptotes and horizontal asymptotes. You can see that on this particular graph we'd have a horizontal asymptote at 0, we'd have a vertical asymptote at 0, and it produces a graph in opposite quadrants. Next we have an absolute value function, and its graph looks like a V-shaped graph, and its equation obviously needs to have an absolute value in it. By the way, on a graphing calculator, if you wanted to graph an absolute value function, you'd go to your y equals screen. You'd have to press the math button. After you press math, you'd have to go to the right 1 to get to the numeric menu, and the first thing listed is the ABS. You'd press enter, and that allows you to put in like an X inside of an absolute value, and that would give you a graph that looks something like this, a V-shaped graph like you can see here. And then our last parent function is called the greatest integer function. And the greatest integer function, it looks like this. We use brackets around an x. And the graph looks like a bunch of steps. And you notice that the steps have closed circles on the left and open circles on the right. And how this function works, it takes the input and produces the greatest integer less than or equal to the input. So as an example, if you put in negative 3.4, the output would be, if you put in positive 3.4, the output would be positive 3. If you put an input of positive 2.8, the output would be positive 2. If you were to put in an output of pi, the output would be 3. If you were to put in negative 4.2, the output would be negative 5. So you're always giving me the greatest integer less than or equal to the input. So we're going to talk about some transformations. Now, here are 2 important rules that you need to remember when it comes to transformations. Anything outside the function affects the graph vertically and logically. I'll talk a little bit more about what I mean by outside versus inside. The second rule is anything that's inside the function affects the graph horizontally and illogically. So a great example of that is this absolute value function. So you can see here that if I put a plus 3 on the outside of the function, that should affect the graph vertically. And so when I graph it, it takes the original graph and moves it up 3. If I go back to the equation, and if I were to have a minus 3 on the outside, that takes the original graph and moves it down 3. If I put the plus or the minus 3 on the inside, and actually let's go with a different number. Let's go with a plus 4 on the inside. Now this is going to affect it horizontally and illogically. You would think the plus 4 moves it to the right, but it actually takes the original graph and moves it to the left. So if we wanted to move it to the right, we'd have to have like an x minus 4. That would take the original graph and move it to the right 4. So that's the first transformation that we'll discuss with these 2 rules. And so, a couple of examples. Now you should be able to do this with the equation as well as with the graph. So this particular equation, if we compare it to its parent function, the absolute value of x, The plus 4 is on the outside. You can see graphically down below. The original one is in blue. The transformed one is in red. And so our transformation is just up 4. The next one, you can see from the equation that the plus 3 is on the inside. If the plus 3 is on the inside, it's going to affect it horizontally, so it's going to shift it left or right. And you got to think illogically. The plus 3 would move it to the left 3. That would be our transformation. And you can see down below, the original graph is in blue. The transformed graph has been shifted to the left 3, which is in red. Part C, we've got two transformations here. We've got the minus 2 inside, so that's going to shift it to the right 2 units, and then the minus 1 is on the outside, so that's going to shift it down 1. So again, these two important rules, they can be applied to all transformations. So these are going to be important to remember and to apply with transformations. More of the same, just no graphs here. So this time we're using a parent function of a cubic, x to the third. And if you look at 2a, we've got a minus 5. That's going to affect the graph. And now you have to ask yourself, is the minus 5 inside or outside? Well, the inside part would have to be raised to the third power. So this minus 5 is on the outside. So that's just going to move it down 5. Part B, we got a minus 3, and you can tell that that's on the inside because that's being raised to the third power. So that's going to horizontally shift it left or right. And the minus 3, you have to think illogically. So it's going to shift it to the right 3. And then the last one, 2C, we've got two transformations. The plus 2 is on the inside, so that's going to move it left 2. The plus 4 is on the outside, so that's going to move it up 4. So this is just describing the transformations from the original parent function to the transformed graph. The next set of transformations I want to talk about is reflections. And so sometimes you can take graphs and reflect them. So the best way to show this is with a square root function. So if I enter the original square root graph, it looks like this, half of a sideways parabola. And if we compare that to a transformed one, if I put a negative sign and then out in front of this square root graph, that's going to take the graph, that's going to reflect it vertically. And you can see here that if you take the blue graph and you reflect it vertically about the x-axis, you would produce the red graph. However, if we were to take that negative sign and not have it on the outside, but instead on the inside, like this, that would take the graph and it would reflect it horizontally about the y-axis. And so you'd take the blue, reflect it horizontally to get this red graph. So keeping that in mind, you're going to have problems like this where it gives you a picture of a graph and it tells you the parent function is x squared. You have to write an equation. Well, you can see that both of these have been reflected vertically. Let's start with example B here. You can see that my transformation is a vertical reflection and then also shifting it up 2. So my equation then would have to be g of x equals negative x to the second and then plus 2. So that would be the equation that would produce this graph. Again, look at that negative sign. That's on the outside. It's not being part of the squared. And then the plus 2 is also on the outside. So both of those are vertical transformations. When you come to part A over here, again, we've got a vertical reflection. And we also have a shift to the right. And that looks like it's about 2.5. So my equation now would have to be g of x equals, we'd have to have a negative sign, then we'd have to have an x minus 2.5 to the second power, and we'd have to have this minus sign in front to make sure that the U-shaped parabola graph is opening down. So that's taking a graph and producing an equation. Here's two more. Again, we're comparing this parent function, 1 over x, to the graph that you're looking at. So on 3a, you can see that there are two transformations. The first transformation is that it's been shifted down 2. And how I know that is because that's where it's flattening out. That's where the horizontal asymptote is. So it's been shifted down 2 because normally the horizontal asymptote's at 2. Sorry, is at 0. And then also there's been a vertical reflection. Because normally the reciprocal function has a graph that's up here in the first quadrant, a graph that's down here in the third quadrant, but you have to take that and reflect it. So that's how I knew it was a vertical reflection. All right, so my equation would have to look like this. G of x equals, we'd have to go with a negative 1 over x, and then a minus 2 per down 2. Well, for a reciprocal function, you guys, the inside part needs to be in the denominator. Everything else is considered to be on the outside. So if we move on to example 3b, can you tell that this has been shifted to the left 4 units? Because that's the vertical asymptote, and normally the vertical asymptote is at 0. So we're going to say that this has been shifted to the left 4. And then again, there's also a vertical reflection. So my equation would look like this. G of x equals, I'd go negative, and I'm going to go 1 over x plus 4. So again, you can see that negative sign's on the outside, the plus 4 is on the inside, moving it left 4. So that would be our equation. Last thing I want to talk about is a dilation, or what I call a stretch and a shrink. We have the same rules that apply, but let's first go to the graphing calculator. And again, this is just a square root graph if you look at that. And so if I were to alter that, the square root of, let's put a, I lied, let's put a 3, let's go with a 4. Square root of x. So you can see here that the 4 is not on the inside, it's on the outside. So what's that going to do to the graph? You can see that the blue is the original, the 4 is on the outside, so it's going to be a vertical stretch by a factor of 4. Here's how that works. Remember our rules. Since this 4 is on the outside, it's going to affect it vertically. And when you're multiplying by a number, it's either going to stretch it or shrink it. You got to look at this value. If the value is bigger than 1, it's going to stretch it. If it's between 0 and 1, then it's going to shrink it. So as an example here, if I replace that 4 with a, let's just go with a 2/3, a number that's between 0 and 1, let's get rid of that 4. Now it's going to take the original graph and it's going to be a vertical shrink. So here's the blue one. If you take it and vertically shrink it, you get one that doesn't go quite as high, the red graph. Let's talk about the horizontal effect. So if we go onto the inside here, and if I put a 4 on the inside, now inside multiplying by 4 is going to have a horizontal stretch or shrink effect. And so you have to ask yourself, what is this value? Is it bigger than 1? And you have to think illogically. If it's bigger than 1, it's not going to stretch it, it's going to shrink it. And so if we take the original graph and you shrink it horizontally, you should get a graph that looks like the red one. And that's going to kind of adjust the curve. Same thing here now if we don't have a 4 inside, but instead we have a fraction such as, let's go with 2/3. So since that 2/3 is a value that's between 0 and 1, that's going to horizontally stretch it. And so the graph, if you take the blue and horizontally stretch it, it should end up looking something like the red graph. So to finish up with here, you're going to be given an equation, and you're going to have to, first of all, identify the parent function. And you can see here that the parent function is just x to the 3rd. And then you have to apply the transformation. That 1/4 is in front, so it's going to be a vertical shrink by a factor of 1/4. And we'll be done. There's the parent function. Here's the only transformation on that equation. Next one, we got 2 transformations. Again, on this one, the parent function would be x to the 2nd. And so the 2 transformations would be a vertical reflection, and then also a horizontal stretch by a factor of 5. Here's how I have the horizontal stretch of 5. This point 2 right here, that's the same thing as 1/5. The reciprocal of 1/5 produces a horizontal stretch of 5. So that's how we go about that. Last example here. Here we have the greatest integer function. And so the greatest integer function is my parent function. And then this particular one is being shifted down 4. Then the very last problem, our parent function would be the reciprocal function, 1 over x. You can see we've got 2 transformations. We got up 3, and we also have a vertical stretch by a factor of 15, because that 15 is on the outside. If it's on the inside, it'd be in the denominator.